Okay, section 11.8 will be all about the binomial theorem and how it works. So you probably read about it, you see some ideas, but let's explain some of the ins and outs about it. So using the binomial theorem, we will be able to expand any binomial that is a sum or a difference, and we will use the binomial theorem to compute probabilities. So knowing that, let's start with this warm-up. If I asked you to take x plus y, the quantity, to the sixth power, most of you should start multiplying. So I'll give you a second. I'll let you go ahead with that. Okay, now that you've finished this, let's just have a little discussion on what you did. Some people said, well, you can't just take, and we've learned that you can't just multiply and say, well, this will be x to the sixth plus y to the sixth. No, I hope we're way past that, because we know that really means I have, and I don't have enough room here, 1, 2, 3, 4, 5, 6 combinations of x plus y. And if we just did 2 of them in our work, we know we would have had x squared plus 2xy plus y squared. Just 2 of them. So that means I would have another one of those and another one of those, and I'd have 3 trinomials that I would then have to multiply out, divide, expand, whatever you want to say. Check your answer compared to mine. Did you get 1, 2, 3, 4, 5, 6, 7 terms in this? And I want you to start looking at them, because this is real important. There's patterns in math. Again, it's just a bunch of patterns and how you undo those patterns. So if we started looking and I said we had 1, 2, 3, 4, 5, 6, 7 terms in this one. I'm just identifying them for our discussion purposes. Some of you are noticing that, oh, the coefficients on the first and seventh terms are 1s. And you have that geometric look because we have odd. So we have a guy in the middle, and then we have that geometric look, which was very similar to what you saw in Pascal's triangle. Nice. Now notice the other thing. Look at your variables. All, yes, different combinations, but remember, alphabetical order, powers rule. So the highest degree comes first, x to the sixth, there are no y's. X to the fifth with 1 y. X to the fourth, y to the second, x to the third, y to the third, x to the second, y to the fourth, x to the first, y to the fifth, y to the sixth. What are you noticing about each and every one of those 7 terms? Nice, I heard it. They all are of degree 6. They have a leading coefficient that's not of degree 6, or sorry, they have a leading degree on the x term, which is not of degree 6, but when you add the degree from the other terms, every single one of them is of degree 6. So that's interesting. 7 terms, all of degree 6, with coefficients that match a row of Pascal's triangle. So if you got all that, we should be able to move on and relate. Instead of multiplying and doing all that multiplying, we can expand much quicker using Pascal's triangle. You got it. So here we go. The binomial theorem says, let n be a positive integer. So we don't care what power you're going to take it to, but it has to be an integer, it has to be positive. So the summation of all the terms in this sequence go from 1 to n. Okay. N is the term, k is that lower one, and we have to do this summation of each of these terms powered with an x and a y. But notice it says n minus k, k. If you just look and put some numbers in, it makes it so much easier for your brain, and you can see what's going on rather than having to memorize all those variable combinations. So take a look here. If I would say whatever n was, and in that last example, remember I had x plus y to the sixth, and I started off with a 6 over 0, then this would have been a 6 over 1, then a 6 over 2, and a 6 over 3, and a 6 over 4, and a 6 over 5. Whoops, I don't want to write the fraction. I keep doing that. That was a 4. And then a 6 over 6 would have been the last term that I could have used. And then look what happens with the variables. And we know that's a combination. 6 things taken 0 at a time, 6 things taken 1 at a time, 6 things taken 2 at a time, 6 things taken 4 at a time. And if you don't like that sort of fractional look, then you can write it like that. You can write it like, whoops, 6 things taken 5 at a time, 6 things taken 6 at a time. You can write them on our combinations. There's nothing wrong with that. But now notice the variables. I will have x to the 6, no y's. Then I'll have x to the 1 less than what I had before. So 5. I'm decreasing the x's and increasing the y's. Going down on the x's, so this would be x n minus 2, n minus 3, n minus 4. And increasing the y's. Y to the first, y to the second, y to the third, whatever y was. So all the way down until I get to no x's and only y's. And that was the pattern we saw. So with that, you should be able to do x plus y to the 9th. And the key piece will be you're going to have to calculate that 9 over 0, that 9 over 1. You can get these. 9 over 2, 9 over 3, etc. You've got quite a few more terms this time. But also you should know some repetition. You're looking for that row. What row were we talking about in Pascal's triangle? That was the key. That was the representation we were talking about. I have to squeeze this last one in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to have 10 things in our 10 terms in that row. Remember up here we had 7. So now we're going to have 10. What can you say about this? You will always have one more term than the power that you're on. Okay, that's easy enough. But those are all combinations. You can do combinations with your calculator to get those coefficients. Yep. Okay. So continuing, once you've found those combinations, and put those back in, there are our 10 terms, and yours should be similar. And we didn't have to do anything with our variables. We weren't multiplying like you were at the beginning of the lesson. We had x to the 9th. You could almost even do this and just put the terms in front. X to the 8th, y, x to the 7th, y to the 2nd, x to the 6th, y to the 3rd, x to the 5th, y to the 4th, x to the 4th, y to the 5th. Right on down, you could have had that set up and just have to finish your combinations or your sequence. If you can get a whole sequence of those terms, you wouldn't have to do 10 separate problems. So you have to decide what's going to be easier for you. But if I would have multiplied this all the way out using the old method, wow, it sure does save a lot of work. You can also see the patterns, see the symmetry again. So here's our middle. There's some more symmetry. We got 5 and 5 on each side. We got 1s on the ends. All right, so this is the sum or difference of a binomial in the form of x plus y, the quantity squared. Well, the technology tip that will allow you to do that. Take a good look. We'll be going over this in class again if you have issues or couldn't find certain keys. This sequence allows you to find anything in this form. It will list all the coefficients for those terms in whatever row of Pascal's triangle that represents. So these are TI 84 calculator directions, so hopefully you have something like them. So second, stat operations. 5 is your sequence. That's what we're doing. In our problem, we have 7 terms. That's why the 7 here. Math, probability. 3 colon NC, because that helps us do the combination. Then it's just x, 0 is where we're starting, going to 7, counting each term at a time. We want them one term at a time, and close that parenthesis and hit enter. I'm looking, When did we open the parentheses? So there might be a typo here. But jot that down, and I will, when we get to class, we're going to go over that again. Another version for your calculator, and check it. If you know how to do some pasting features, you could use that. So a quick way to get those coefficients, and again, we will show that in class. So now the question is, well, what happens if, and I actually want to bring this up here, what if now I don't have an x minus y combination? I've got a number sitting there. You can apply this binomial theorem to the expansion of a sum or difference of two monomials. It does not matter what they are. So instead of x and y, which is our focus last time, to the sixth power, we can now start thinking, well, that negative 2 really is our y. So I have 6, so there's 6 over 0, 6 over 1, combination, 6 over 2, 6 over 3, 6 over 4, 6 over 5, 6 over 6. But now, instead of xy, our factor, or our value, was a negative 2. So I'm taking x to the 6th, negative 2 to the 0, x to the 5th, negative 2 to the 1st, x 4 and 2, 3 and 3, 2 and 4, 1 and 5, 0 and 6 gives us the combinations. We got that negative 2 hiding out in each and every single one of them. Yes, it will be a number. Yes, that number will have to be used, calculated, put in a little differently because we never had to touch the y's before. So here we go. With our combination, after we calculated our Pascal's triangle combination, we have a 1, 6, 15, 20, 15, 6, 1. Then we go to our math here and say, oh, we know negative 2 to the 0 is, anything to 0 is 1. Negative 2 to the first is a negative 2. Negative 2 to the second, negative 2 to the third, negative 2 to the fourth, negative 2 to the fifth. So we're also doing the math on the 2's. Once we do that, we can see all we're going to have for variables is our x's. So in this case, the exponents don't always have the same degree power. We've got our going down in descending order, 6, 5, 4, 3, 2, 1, 0. But we're going to have to put all these numbers together because numbers always go out front. So on the first term, we have nothing to change. But on the second term, that negative 2 times our 6 gave us negative 12. The 4 times the 15 gave us 60. The negative 8 times 20. The 16 times 15, the negative 32 times negative 6, and the 64 times 1. So double check it when you finish. You want to make sure you are in descending order, highest to lowest according to the exponents, and we only have that 1 on the x, and that should do it. That saves you a ton of multiplication because you now see that we have a relationship to the binomial theorem. Ah, good. Shortcuts. So now you try this one on your own, and we'll see what happens. So give you a second or two to work on that. This time it's an x minus 2y. So I kept the y in, and I have a 2. So it's going to mirror this one quite a bit, but it's only to the 5th. So we got one less term than before. So a lot of your work should generate the same way. Pause if you need time to work on your own before showing the answer, or jot the answer down and then go back and work. Here is that final combination. And again, on this one, they will be degrees of 5 all the way through. But that 2 was incorporated also. Symmetry in the beginning, but not in the final one because of those powers of 2 that had multiplied, which is the same thing we saw up here. Okay, last but not least, let's see. We should be good to go. That's the nice part. So one more time, here's that if you were looking for that answer. And so bring any questions you have to class, especially about generating the combinations. We'll go over that again and check on that calculation sequence that I gave you.